All right, let's try to make the square root function less problematic than it has been for us. The way we're going to do that is by exploring what the complex square root function ought to do, how it ought to behave, how ought we choose, or how can we choose the domain of the non-one-to-one complex square function in such a way that renders it one-to-one and therefore gives it an inverse function which we can call the complex square root. In this video, I want us to be able to land on the definition of what's called the principal square root function for complex numbers. This is going to be, in a sense, the canonical way that we've defined square roots that should agree with the ordinary way that we define square roots of non-negative real numbers in the high school classroom. But extended up into the complex plane, we'll have an opportunity to see what those behaviors should be like. So what changes and what remains the same. So to get started, I want to take us back to this idea that complex functions, just like real functions, many of them are not one-to-one. They can be many-to-one, right? And so if we want them to have inverses, if we want to even have left inverses to begin with, we need to restrict them to a domain on which they are one-to-one. So here's a definition. When you hear someone speak of a branch of a function, what we're going to mean by a branch of a complex function is a choice of domain. So it might be a smaller domain than the entire complex plane. We want the function to be one-to-one on that domain so that we can define the left inverse that we would want, right, and have a hope that our function is invertible. But then the second thing we want is we want the domain to be chosen as large as possible so that we are as close to this function being onto as well as possible so that we can define the inverse, we hope, on as much of the complex plane as is possible. So here's the idea behind how we can choose a branch of a complex function. What we want to do is we want to somehow separate points that f doesn't separate. So let's think about that in the context of the squaring function f of z equals z squared. What kinds of pairs of points does f have trouble telling the difference between? Well, just like in the real case, the squaring function for complex numbers cannot tell the difference between a complex number and its additive inverse, its opposite, z and minus z. That distinction exists before we process through the squaring function, but then is lost when we process through the squaring function as an output. So f of minus z and f of z are the same. Therefore, in order to make this function one-to-one by choosing a smaller domain for it, what we want to do is pick a domain that does not contain the opposites of any of its own points. So what might that look like? So here's a visualization of the complex plane with some input points inside of my purple circle, and then we can kind of see what the output points are in the green curve. Right? So I can kind of play around with this. As I move my purple domain around, I can see what the green codomain, the green range, ends up looking like, right? And so we end up getting one-to-one functions here, for example, right? As I sweep this ray through my circle, I can watch the image of that ray get swept through the image of that circle. And it looks like my function is one-to-one. There's no way for two different inputs inside of my purple disk to give me the same output inside of my green area. And so in order to have a domain on which the squaring function is not one-to-one, maybe we need to do something like this. I'm going to zoom in a little bit so we can see more what's going on. If I restrict the domain of my squaring function to this purple disk, now what we notice is that here is an output of my function. Notice how the output curve here, the image of my circle, my purple dotted circle, is this green dashed curve. And there's actually 2 points on my original purple circle, this one and also this one, that give me roughly the same output in this function. So now we're not one-to-one anymore because the squaring function is kind of wrapping this circle over itself in a portion of the plane. And again, the reason for that is that this domain, this purple shaded disk, contains both some z's and their own opposites. And as soon as those two get processed through the squaring function, they end up giving us exactly the same output. So how do we make the best choice that we can make? Well, the way to do that is by choosing what we would call an open half plane through the origin. So what does that look like? Well, if I choose my domain to be, let's say, the entirety of the right half plane, so all of the complex numbers whose real part is positive, greater than 0, then when I square any one of those z's, I'm going to get some square w, which is going to be one of my outputs, right? And wherever that output is, I can also go backwards, right? So this function is going to be one-to-one on this domain because, for example, if this is my w, I'm trying to go backwards from down here, I'm going to go backwards to this copy of z and not that copy, because that copy is not part of my original domain. So this half plane that we're shading on the right half of the complex plane does not contain any z and also its opposite z. And therefore, my function can be one-to-one. My squaring function can be one-to-one on this domain. This is just like in the real case a little while ago when we restricted the domain of the real squaring function to be only non-negative numbers, because then that makes it so the squaring function is one-to-one on the non-negative real number. So we're only getting half the parabola. This is the complex function analog of doing that. We're picking just the right half plane so that whenever I take the square root of any number that's possible to take the square root of, the answer that we're going to get out of that inverse is going to be something which has a positive real part. And its counterpart, the opposite of that has a negative real part, we're just going to throw away when this is our choice of restriction of domain. So that's how we can kind of get started, but it's not the only choice that we could have made. When we were looking at the real square root function a little while ago, we looked at the two different inverses that are created by picking the non-negative real numbers as the domain of the square function on the one hand, and therefore the traditional square root is the inverse, or choosing the non-positive real numbers as the domain of the squaring function gave us a different inverse function, which was minus the square root, right? And so we can make a similar set of choices in this case. So instead of picking the right half plane, I could have picked, let's say, the left half plane. Let's see, how do I do that? Here we go. I could have picked the left half plane. And if I do that, now the square root of, let's say, the square root of 4, so 4 would be this point, the w point here on the positive real axis. Let me add in our axis numbers just so we can kind of see what's going on. The square root of 4 with this choice of domain of my squaring function would now be negative 2 instead of positive 2, because that's the domain that we're coming from, right? And similarly, I could take the square root of, let's say, 4i. Can I get there? Yeah, the square root of 4i. Would be this complex number in the third quadrant of the complex plane. It would have negative real part and negative imaginary part, right? And not the one which is in the first quadrant over here. So again, any half plane that I pick through the origin is going to succeed in separating z from minus z, and therefore enabling me to define a single-valued inverse for the square root function. And this dotted line, which defines my half plane, once I apply the squaring function to it, is going to give me this sort of dotted ray through the origin. And so the range of this function is going to be the entire complex plane except for this green dotted line, which is taken out of it. So in the case of picking the right half plane, we're sort of removing from the codomain of my squaring function the negative real axis, right? So there's no way for me, right, to square a number from the open right half plane and get a number that's on the negative real axis, right? I can't make the w land on the negative real axis in some way, because in order to do that, I would need to pick a point from the positive imaginary axis. So this is how to choose a branch, if you like, of the squaring function to render it one-to-one and also have a maximal codomain, right? There's no way for me to enlarge the domain in any way that sort of fills in this ambiguity. Well, there's a little bit of a way. We're going to look at that next. So let's get an introduction to what we would think of as the canonical choice for a square root function. And that's called the principal square root, or the principal branch of the square root function. So there is kind of a way to choose a branch, in other words, choose a domain for our original squaring function in a nice enough way that allows our square root to be a single-valued function, and for the square root to agree with the traditional square root of real numbers that we learn in the high school curriculum. And to do that, we just define the principal branch of the square root using the polar form of a complex number z. And we define the principal square root of z to be the number w, which has modulus equal to the square root of the modulus of z. So it is sort of its distance from the origin gets square rooted, if you like, in the complex plane. And the principal argument of the square root is half of the principal argument of z. Right? So it square roots the modulus, and it cuts the principal argument in half. Now, I'm using the word principal in front of argument for a good reason. And that's because the way that we define the principal argument, we're using principal in the same way here, of a complex number, was that the principal argument is always an angle between minus pi and pi, but if we happen to choose a number that's on the negative real axis, we still give it an argument, and the argument we give it is positive pi rather than negative pi. Right? So the number negative 10 would have an argument of pi rather than an argument of minus pi. So that's a way to resolve the ambiguity that would otherwise happen on the negative real axis. So this is the principal branch. Let's take a quick look at how it works. Let's suppose that I start with a non-negative real number. What would the principal square root of that non-negative real number be? Well, so if I start with the number 16, right, 16 plus 0i, its modulus is equal to the square root of 16 squared plus 0 squared, so the modulus is equal to 16. And its principal argument is the angle between minus pi and pi, inclusive of pi, which measures the angle from the positive real axis. Well, this number is on the positive real axis, and so its angle, its principal argument, is 0. So to find its principal square root, we'll take the square root of its modulus to get the modulus of the principal square root, and that's going to be the square root of 16, which is 4. And we cut the argument in half, but the principal argument was 0, and you cut that in half, and you get 0 again. So what is the principal square root? It has modulus 4, principal argument 0, and so in rectangular coordinates, it's 4 cosine 0 plus I times 4 sine of 0, and that's 4. So the principal square root of the complex number 16 is the complex number 4. Secretly, what that means is that the way that we prefer to define the positive output square root of a real number in high school agrees with our choice of the principal square root of a positive real number when we're in the complex plane. So that gives us a little bit of a reality check, that when we define the principal square root, we're making a choice, but it's the same type of choice that we would have made in the high school curriculum when we prefer the positive valued square root over, say, the negative valued square root function. So what about a negative real number? Let's say I take negative 9. What would the principal square root of it be? Well, negative 9 as a complex number has a modulus equal to 9, square root of negative 9 squared plus 0 squared. And because it resides on the negative real axis in the complex plane, its principal argument could have been negative pi or pi, but again, because of the definition of principal argument including pi and not minus pi, we assign pi the principal argument of this complex number. So its principal square root takes the square root of the modulus to turn it from 9 into 3, and it cuts the argument in half to make the new argument pi over 2. And so in rectangular coordinates, the principal square root of negative 9 is 3 cosine of a half pi plus I times 3 sine of a half pi. And since the cosine of half pi is 0, sine of half pi is 1, we get 3i. So the principal square root of negative 9 is 3i. In particular, this also means that the principal square root of negative 1 is the traditional positive coefficient imaginary unit that we call I. So in our very first videos for this course, I avoided saying that I is the square root of negative 1 for this reason, because what I is it's the principal square root of negative 1. Negative 1 has multiple square roots, right? It could be I or it could be minus I, but when we use the principal branch of the square root function, we are privileging I as the principal square root of negative 1. So to wrap this up, let's tie it back into this domain and codomain question. What are the codomain and the domain of the principal square root function? In other words, where are the z's coming from that I can take the principal square root of? Well, it looks here like my z's can have any argument, any principal argument that I like, and if the argument is strictly between minus pi and pi, so in other words, if I don't pick a z that's on the negative real axis, then it's pretty simple to see that when I cut its argument in half, I'm going to get something which is in the open right half plane of the complex plane. So this is the original sort of example that we looked at a couple of minutes ago, right? So then the question becomes, what happens if I want to take the principal square root of a negative number, something which resides on this negative real axis? Well, if it resides on the negative real axis, the principal square root of a negative real number, we have sort of agreed here by the definition of principal square root that it's going to give me a number that's imaginary with a positive imaginary part. Because when I take the principal argument of one of these negative real numbers, the principal argument is positive pi, so when I cut it in half, I get positive pi over 2, and that means that the image is going to be on the positive imaginary axis. So this is what the principal square root function can do. Actually, its domain, we can take the principal square root now of any complex number at all. The domain of the principal square root function is the entire complex plane, which is super cool, right? But there's a limitation to the principal square root function. Even though its domain is the entire complex plane, you'll notice something kind of interesting happens. If I take a loop, let's say around here, it looks like my outputs are moving smoothly with respect to my input. But what happens when I try to cross over this negative real axis? Suddenly my output jumps, right? As I go from one side of this axis to the other, the output of the principal square root function is suddenly jumping from having a positive imaginary part to having a negative imaginary part. And so in particular, what that's going to mean for us is that, yes, while the principal square root function is nice and all, it turns out not to be a function which is continuous on the entire complex plane. It's continuous in most places, but for any neighborhood of this negative real axis, which we call a branch cut for this square root function, in any neighborhood of this negative real axis, our function's not continuous. Because as soon as I go from one side of this negative real axis to the other, the imaginary part of my output is going to suddenly jump from positive to negative, or vice versa. So this is how the principal square root function behaves. And it gives us the ability to take the principal square root of any complex number, including the ones which are negative real numbers. It's just that we privilege here the square root of a negative real number. We privilege to have a positive imaginary part, and that choice creates this weird jump discontinuity as we go from one side of that branch cut to the other. So that's the story of the principal square root function and how inverses for multivalued functions can work in complex variables. That's probably where we're going to have to end this week's material. And I want to kind of draw out what we're going to do next just a little bit, because there's going to be a lot to chew on. Now that we have this introduction to how the square root behaves in a special fashion because the square function was multivalued, as you might imagine, this problem, this opportunity, this behavior extends to all power functions of a complex variable as well. And so some of the traditional rules that we take for granted about exponents are going to end up being broken. We already sort of saw an example of that previously in this square root of -1 times -1, splitting apart the square root over the product and turning it into I times I, and thereby proving that 1 was equal to -1. Something went wrong there algebraically, and that something relates to how we have to think a little bit differently about even just taking the exponents of complex numbers when I interact that exponentiation with other kinds of arithmetic. What other rules are going to be on the table for being broken, and how can those new rules help us to understand the complex exponential function? So that's what we're going to shift gears to, but we're going to save that material for where we get to next week.